So in last reaction, we looked at where electrophile was halogen. And now we're going to look at a series of reactions where electrophile is some kind of carbonyl compound. All right. So the first reaction that we're going to look at is called Aldol reaction, and it proceeds in several steps. So we're going to look at the first product first, which is an aldol addition reaction, and then we're going to take a look at what happens to that under different condition, which is the dehydration of the aldol addition product. So initially, when we talk about aldol addition reaction, what we're going to do is have an aldehyde and react under a base, not a very strong base, but a weak base in terms of the pKa of the aldehyde. Alpha proton is, remember, the aldehyde is like, the alpha proton is around 20, hydroxide is around 16. So when you deprotonate and form an enolate anion, which is shown here, where it grabs a proton and then makes the anion at the alpha carbon, and this is a resonance that is showing here, whereas O minus and the double bonded here. So this enolate ion is in equilibrium with the starting material, right? So this is crucial, important point that you need to be aware of, that under this condition that we're looking at, both the aldehyde, so unreacted aldehyde, and the enolate is present at equilibrium. So this represents our nucleophile, the enolate, but it's in the presence of the carbonyl, and as we know, the unreacted carbonyl it could also serve as an electrophile, as we've seen in unit 2 and 3. So the reaction that we're about to look at is a self reaction in which the aldehyde becomes an enolate, but not all of it becomes an enolate. Portions of it becomes enolate in equilibrium with the unreacted aldehyde. So we have a nucleophile and an electrophile present at the same time, and that's the reaction that we're about to go over. So we have the enolate that is now reacting with unreacted aldehyde. All right, so what's going to happen is it's going to make a carbon-carbon bond formation. And this is why aldol reaction and the reactions that we're about to go over are very important, because it's making a carbon-carbon bond. So the enolate carbon is going to be the nucleophile. It's going to go and attack the electrophilic center, which is the carbon of the carbonyl, breaks open the C double bond O. You've seen this chemistry in unit 2 and 3. It's just that here the nucleophile is going to be the enolate. So then what happens is you're going to form a carbon-carbon bond. So make sure you draw a dash between these two carbons, and then you have an alkoxide anion present. And then what's going to happen is, after that, it's going to in the third step, grab a proton to regenerate the hydroxide ion, and what you have is an aldol addition product. And the reason why it's called aldol is because the product has the aldehyde and the alcohol in which it has added. So the aldehyde and the ol stands for the alcohol. So it's really representing the product that you get. And this actually occurs a lot more readily for aldehydes, but for ketones, the equilibrium for this reaction lies to the left. In other words, there's a lot more of the starting material present when you start with ketone than product. But for aldehydes, this happens readily, and this aldol product is what is the final product if you keep it at this temperature. All right. At this point, you should be able to do 22.15 and 22.16, which is really going over what the products look like given a starting material, so you get used to drawing these. The product that you get is often called, so this carbon next to the carbonyl is the alpha carbon. And notice the where the OH ends up is in the beta carbon. So a lot of times this is called beta hydroxy carbonyl compound. That's sometimes referred to as the aldol product. All right. So once you're able to give me the products, what we're going to go over next is what happens to these compounds if you allow the reaction to heat, or allow reaction to react further by providing heat. All right. So what happens is that the second step of the reaction occurs in which the condensation occurs. Condensation is referring to reaction in which a small compound is basically removed. So water in this case is what's removed from the starting material, and what happens is basically the alpha proton is removed by the base, and then the double bond forms and regenerates the OH minus. So the alpha hydrogen of the beta hydroxycarbonyl in the second step, which is the dehydration step, or another name for that your book talks about is condensation reaction, where proton is removed, at the same time the double bond is formed. All right, so the draw another bond to indicate the double bond forming, and then the OH minus is extruded as a to regenerate the base, and the water is formed as the byproduct, which is where the name condensation comes from. So this double bond is actually in conjugation with the C double bond O, and these products are called alpha beta unsaturated carbonyls. And they're more stable than the beta hydroxy carbonyls because of the resonance stabilization. You could see how you could draw a resonance with the double bond and having the C double bond O pi bonds, pi electrons participate, right? So that's the final product if beta hydroxycarbonyls are heated. And some of the problems that you are asked to do in the drill is give aldol product when the following reacts in an aldol condensation reaction. So when it asks for aldol condensation reaction, that means that you're having a base and then you're providing a heat so that it's not stopping at the beta hydroxycarbonyl, but it's moving on to the final product, the alpha beta unsaturated carbonyl. If it asks for aldol addition product, then you would stop at the beta hydroxy. All right. So these three compounds, I know that the yield for these ketones are not high, but just want you to be able to draw carbon-carbon bond formation regardless of what you start with, and be able to give me the products of that. All right, and then from your book, if you could do 22.20, that will also give you some practice in figuring out what the product might be before we start doing synthesis problems, which we'll be looking at later. All right, so that's aldol reaction, and probably the most challenging thing about the doing aldol reaction is basically you need to draw out both the starting material in the enolate form and the unreacted, and actually draw the arrows to be able to make the carbon-carbon bond easily until you get really used to being able to come up with these products. All right, and one of the side things that I want to talk about is when you form a alphabet unsaturated compound, the double bond, if it's in the trans form, like this methyl group is in trans form with this group, so that the hydrogens are also trans. So if the two big groups are in the trans, that's going to be a lot more stable because of less steric hindrance than if they're cis to each other. So a bigger the R group, you tend to only find products in which the double bond is in trans form, not cis form. All right, so that concludes this lecture, and hopefully you will be able to do some problems like this. And so I got 1 minute left, so I'm gonna let's see, do one problem. Draw the condensation product. So this is 22.20. Let's try E. So we have this compound, and the reason why I chose this because a lot of times students have problems with cyclic compounds. So you're doing a self-condensation reaction of this. So pretend that you have an enolate plus you have unreacted starting material. So you're going to go and react at this carbonyl. So I highly recommend drawing out until you could do it without doing this. So you're making a carbon-carbon bond, which I'm highlighting with this carbon and then this carbon, which is part of the ring. So this is going to have OH now, right? And that's going to be part of a 5-member ring, in which that's attached to the benzene ring. All right. So then if this dehydrated, so in other words, I mean, you could think of it as water being removed here. So draw everything exactly the same way. Remove OH and H, put a double bond between this carbon and this carbon. I don't have time to draw this, so I'm going to stop here, but that would be the final product.